Alright gang, here we go. These are the practice problems that we did in class on Tuesday and Wednesday. So number one, we have a dragster. It's given us the final velocity and the initial velocity. It's starting from rest, remember. It also gives us the time. So we plug in our values here into the equation for acceleration, and we can solve for the acceleration in part A. Part B is asking for the magnitude of the force during this time. Recall that force is equal to mass times acceleration. So I can take the mass of the dragster times the acceleration of the dragster that you got in Part A. Part C is asking for, it gives you the driver's mass, and it says what horizontal force does the seat exert on the driver. Well, the seat is accelerating at the same speed as the rest of the car, so we can just do another Newton's second law. Mass times acceleration to get the force. But this time, use the mass of just the driver and then the acceleration of the car, which is the same as the acceleration of the seat. And then we get our answer there. Question number 2 is asking for the force that's applied during this time interval. And anytime there's a force, there's an acceleration. So here what I did first was I found the acceleration. And the way I did that was I was given a final velocity, I was given an initial velocity, I was also given a time. So I can plug into that equation for acceleration to solve for the acceleration of the car. Now I can find the force by using Newton's second law, F equals ma. We're talking about the mass of the car and then the acceleration of the car that we just found. Question number 3, we have a swimmer who's jumping off and we need to find the velocity when he hits the water. So I can use my VF squared equation here. Remember, the velocity final here in this equation, the velocity initial here is 0 because we're just starting from a diving platform or whatever. We're starting from rest, then we're jumping off. And the acceleration here is 9.8 because it's gravity. When you're free falling, the only acceleration that you experience is gravity. And then I got the number 10 there because we're given the height of the tower, which is 10 meters. So I solve for velocity final. Don't forget to take the square root, and you get 14 meters per second. Now, for part B, we want to find the force exerted by the water as the swimmer slows down. Before we can find force, we need to find acceleration. So we're going to find the acceleration that the swimmer experiences once he hits the water. The velocity final is 0 here because we're talking about when the swimmer comes to rest, and the velocity initial is 14 because when he hits the water he's going 14 meters per second. The acceleration is unknown, that's what we're looking for, and the d is 2, that's given in the problem. It says he goes 2 meters before he comes to a stop. So we can solve for acceleration here. And then we can take that number and we can plug it back into F equals ma using the mass of the swimmer in order to find the force exerted on the water that brings your swimmer to a stop. Now, I had a negative acceleration here for part B, and I had a positive force. That's sort of a convention. A lot of scientists tend to use positive numbers for force, even though it would really be negative if you plugged in a negative for the acceleration. So if you're confused by that, I apologize for not being super consistent, but it tends to be a convention to use the negative sign to denote direction for velocity and acceleration, while we tend to make the force positive no matter what, to take the absolute value of that. So try to just focus on the magnitude for now rather than the direction, but I'll do my best to be consistent. Number 4, we're given the weight of a motorcycle. Recall that a weight is a force. The weight is the mass times acceleration of gravity, always. And so to find the mass, I can just rearrange F equals ma to solve for mass. 9.8 is my acceleration, and there's my answer. Number 5, we have a helicopter that is moving upwards. And we're given the mass of the helicopter. So let me pause here for a second. The first thing I did was I found the net force exerted on the helicopter. We're given the mass of the helicopter, 4,500 kilograms. We're given the acceleration of the helicopter, 2 meters per second. So the net force of the helicopter is 9,000 newtons. Now, in addition to that, we have a force of gravity that's pulling down and a force of lift that is pushing up. And we need to find the lift that is pushing up. Let me say that one more time. We have a net force on the helicopter, what is actually happening, and that is the 9,000 newtons. What's actually happening is the 4,500 kilogram helicopter is accelerating upward at 2 meters per second. So the net overall force is 9,000. However, the components of that force are force of gravity down and some force of lift in the up direction. And the question is asking, what is that lift in the up direction? Well, I can find the force of gravity in the down direction because I know the mass and I know the acceleration of gravity. So here's my force in the down direction. In order to find my force of lift in the up direction, I need to sort of write out my equation here for the net force. The net force is going to equal the force of lift minus the force of gravity, because the force of lift is going up and gravity is going down. So here I have written in the numbers here. We can rearrange, solve for the force of lift, which is written there. Number 6, we're driving a car and then we're slowing down, and the question is asking for the force of friction. Before you can find force, you need to find acceleration. Always. Don't just jump straight to the force. We can't find force unless we find acceleration first. So there we go. The velocity final is 0 because we're coming to a stop. Velocity initial was given. The distance was given. I solved for A, and I got negative 3.92 meters per second squared. Now we can find the force because we have our acceleration, and the mass is given in the problem. Okay. Number 7. This one's really tricky. Mr. Warner's standing on his bathroom scale. So the first thing I want to do is find the mass of Mr. Warner. Now let me explain to you how I did that. I know that, excuse me. Turn my phone off for a second. Okay. We're given the weight of Mr. Warner. Remember, weight is a force. Weight is the force of gravity. So if I'm given the force of gravity, which is given as 836, and I know the acceleration of gravity, which is 9.8, I can find the mass. Remember that weight is the force of gravity. So I rearrange that, I solve for mass, I get the mass is 85.3 kilograms. Okay, cool. So when we accelerate upwards, when the elevator begins to move upwards, we have an adjustment to our net force. Our net force when we were just standing there was 0. Let me pause this for a second. When you're just standing there at the bottom of the elevator not moving, your net force is 0 because, oh my god, your net force is 0 because the normal force pushing up on you is equal to the force of gravity pushing down on you. But as soon as the elevator begins to move, your net force is not 0 because you're moving. Anytime you have some sort of acceleration, your forces are unbalanced. In this case, the net force is 100 newtons. I've calculated that for you by taking the force in the upwards direction, which is 936, that's given in letter A, minus my resting force, which was 836. So my net force is 100 newtons in the up direction. So I know my net force, I know my mass, which I've calculated, and so I can plug that in to find the acceleration in the up direction. And here we go, the acceleration is 1.17 meters per second squared. The next part is asking you to find the acceleration when you come to a stop. So now I've calculated the net force to be negative 54 newtons because my resting force is 836 newtons, that's given in the beginning. And now at letter B it's saying that the scale drops to 782. So now I'm under my resting force. I have some sort of negative net force. I'm slowing down. So the net force is negative 54 newtons in this case, 54 newtons less than what it normally is. And I know the mass of Mr. Warner still, that has not changed. So I can just plug that in to solve for the acceleration. In this case, it's going to be a negative number, which makes sense because you're slowing down. When you arrive at your floor in the elevator, you're slowing down. And part C is asking which would take a longer time, the starting or the stopping. Well, if you have a larger acceleration, you can achieve your velocity in a smaller amount of time. If you have a small acceleration, it will take you a larger amount of time to reach your velocity. So stopping takes longer because the acceleration is a smaller value. Okay, so number 8. Hold on, I need to pause this for a second. Okay, sorry about that. Here we go. Number 8, we have a balloon. And we're given the force in the up direction of the balloon, and we can calculate the force in the down direction of the balloon, because the force in the down direction is the force of gravity. The force of gravity is equal to mass times acceleration. We're given the mass. We know the acceleration due to gravity, so we can calculate the force. So now we can find the net force because we know the force in all directions. We know the force up is 98 newtons. We know the force down is 49 newtons. So we can find the net force, the sum of the forces, the total force, by taking the difference between these two. And then, of course, we set that to mass times acceleration, Newton's second law, and then we can find the acceleration. Let me just stop there one more time. I want to clarify this. When you have multiple forces acting on a system, you need to determine the net force, the total force, and then set that equal to the mass times acceleration of the whole system. So I added up my individual forces, and when I add them together, I get 98 minus 49. Now I can set that equal to the mass times acceleration of the system. The mass of the system is 5, and the question is asking the acceleration of the system. And the answer is 9.8 meters per second squared. I forgot the squared. This is not the acceleration due to gravity. It is pure coincidence that the value is 9.8. Part B is asking for the velocity of the instruments the moment that they release. So I can use this equation here. The velocity initial is 0 because they start from rest, presumably, unless they say otherwise. My acceleration is 9.8 upwards because this is not gravity. This is just the answer I got from part A. And the time is 10 seconds. That's given. So I solve for velocity final after 10 seconds, and the answer is 98 meters per second. Part C is asking for the net force acting on them after their release. Well, the net force acting on anything after it's released into the air is going to be the force of gravity. As soon as the instruments are released from their balloon, they're free falling. They're going up because they have that upward motion. They've been released. They're still going up for a little bit, but the only force acting on them is the force of gravity. You can still go up and have a force of gravity in the down direction. When they're just flying through the air, not attached to anything, the only force is the force of gravity. So the force of gravity is equal to the mass times the acceleration of gravity. And the answer is 49 newtons. Part D says, when does the direction of the velocity first become downward? So here I set my velocity final equal to 0, because the moment when the velocity becomes downward, the moment when it stops going up and starts going down, the velocity is going to be 0, just for a little bit, but it's going to be 0 for that split second before the object starts falling. The velocity initial I calculated previously, 98 meters per second up. The acceleration is the acceleration of gravity, which is down, and then I'm solving for t. So I can plug it all in, and then I get my t equal to 10 seconds. Number 9, we have 2 people pulling on a rope. We're given some masses here and some accelerations. And so we can calculate the force of the girl, because we're given the mass of the girl, which is 45 kilograms, and we're given the acceleration of the girl, which is 3 meters per second squared. I plug that in, I can calculate the force of the girl on the rope, or the force of the rope on the girl, same thing. So 135 newtons refers to the force of the girl on the rope, or the force of the rope on the girl. Now, let's think about the force on the boy. If there's 135 newtons of force pulling on the girl, then if the boy is touching the same rope, he is also experiencing that 135 newtons worth of force, because it's the same rope and the tension in the rope is uniform. So the force of the boy is also 135 newtons. It doesn't change because it's the same rope. Now we can plug that into Newton's second law and solve for the acceleration of the boy, which is going to be different. His mass, 65 newtons, is given, so I just plug that in to solve for acceleration, which is 2. So it's the same force, it's the same force, but in the opposite direction. So, and this is confusing, because a lot of people think, well, when I'm playing tug of war, I don't feel the same force. If I'm winning, I'm feeling more force than the team that is losing. Or maybe you feel like if you're winning, you're feeling less force than the team that is losing. But that's not true. What you feel is acceleration. You feel acceleration. The force in the rope, whether you're playing tug of war against the football team or against the Pee-wee baseball club, is the same throughout the rope. The force is the same throughout the rope. The only thing that changes between the different people is the acceleration. Let's take a look at number 10. First, we need to find the acceleration for part A. So I can plug that into my equation for acceleration here. I'm given the change of velocity in the problem. I'm also given the time in the problem, so I can just plug that in, solve for my acceleration. Very high number, because the baseballs, they're moving pretty fast. Part B, the force acting on the baseball. Well, I have my acceleration, and I have the mass given in the problem, F equals ma. Plug those in, and I can find the force of the baseball. The reason I use a negative value here is because we had a negative acceleration in part A, because the baseball is slowing down. So my force would also be negative. Okay, so now I realize now I might be being inconsistent. There's two ways to write it. You can either say 870 newtons in the negative direction, or you can use the negative sign there, negative 870 newtons. But really the most important thing with the signs is the velocity and acceleration. Part C, the magnitude and direction of the force acting on the player who caught it. Well, if the ball experiences a force of 870 newtons in the negative direction, then the player experiences 870 newtons in the positive direction, because Newton's third law states that opposing forces are equal and opposite. That brings us to number 11. This is a scary problem at first, and the way to make it less scary is to break it down into its individual components and then piece them back together slowly and carefully. So we have two blocks here slung over a pulley. First it says to sketch the problem, then it says to create free body diagrams. I'm going to do that in yellow here. On the mass on the right, we have force of tension in the up direction. We have force of gravity in the down direction. I abbreviated that F sub G1 for the force of gravity on the 1 kilogram block. Let's look at the 4 kilogram block. I have a force of tension in the up direction. I have a force of gravity in the down direction. I'm going to denote that FG4. Okay, so each block experiencing two opposing forces, and it's important to write them all down. Next, let's talk about just the sum of the forces on mass 1. So I'm not talking about the whole system, I'm only talking about mass 1. The sum of the forces, the total of the forces, the net force, is the force of tension minus the force of gravity. So I can say the force of tension minus the force of gravity equals ma, because the sum of the forces equal mass times acceleration. Now, how did I know that to do force of tension minus force of gravity instead of force of gravity minus force of tension? Well, you could do it the other way. There are ways to do that, and we can talk about that if you want. But the reason I chose this direction is because I like to think about the direction that the blocks are moving. Look at the whole pulley for a second. The 4 kilogram mass is heavier, so it's going to go down, and the 1 kilogram mass is going to go up. So because the 1 kilogram mass is going up, the sum of the forces are tension minus gravity, because tension is going to be greater. Let's just say, I don't know, let's say the force of tension is 10 and the force of gravity is 5. We want the total force to be a positive number because it's going up, so we want to do 10 minus 5 to get a positive value. So look at the direction that your objects are traveling and write your sum so that your force is positive. So I chose to do force of tension minus force of gravity because it's moving up and I want to have a positive net force. So you take your sum of the forces, you set it equal to mass times acceleration here. I'm going to plug in some values. We know the force of gravity because we have the mass, and then we have mass again times acceleration, which is unknown. I do not know the acceleration. Let's look at the sum of the forces on block number 4. Sum of the forces equal to mass times acceleration. Here we go. The force of gravity minus the force of tension equals ma. Now, how did I do that? How did I know to do force of gravity minus force of tension? Why did I not do force of tension minus force of gravity like I did for the other one? Well, this one is moving a different direction. This one is moving down. So the prevailing force, the stronger force, is the force of gravity. So if I want to stay consistent to my idea of having a positive force, then I do the greater force minus the lesser force. If it's moving down, the greater force is gravity, and the lesser force is tension. So the sum of my forces are going to be the force of gravity minus the force of tension, and set that equal to mass times acceleration, Newton's second law. So what I'm doing here is I'm taking the individual components and writing out the sum of their forces, and then setting that equal to mass times acceleration. And that's how you solve these problems that have more than one thing going on. If it's more than just one thing, more than just one dragster or whatever, then you got to write out the sum of the forces on each individual component and set it equal to mass times acceleration of that individual component. So let me plug in my numbers here. I have the force of gravity. I have the force of tension is unknown. My mass here is 4 times acceleration. So notice that in each of these cases, I set the sum of the forces equal to mass times acceleration, but I have a different mass in each one because I'm just talking about the individual components. Now, in my lavender color pen here, let me rearrange that first expression for force of tension. So I'm just rearranging my equation here to solve for the force of tension. I didn't do any math yet. I just rearranged it. Let me also rearrange my bottom expression for block number 4, or rather the 4 kilogram block, with also my lavender pen. Let me rearrange, solve for f of t. I'm not doing any math yet. I'm simply rearranging and solving for f of t. So why did I do that? Well, we got too many variables here. In each of these, we have an f of t and an a. And you can't solve an algebraic expression if you have 2 variables. So the reason I rearranged for force of tension is because the force of tension in each case is the same, because they're the same rope. They're 2 masses hung on the same pulley, the same string. So because it's the same string, the force of tension is the same. So I can solve for force of tension and set them equal to each other. You could also do this for acceleration. Because they're attached to the same string, they're going to accelerate at the same rate. One's going up, one's going down, but it's going to be the same value. So I could just as easily solve both of these for A. It would take you a little bit longer to get to the final answer, but you could certainly do that. So now I'm going to take these 2 things that I circled and set them equal to each other on the next slide. Now, the only thing I'm doing here is I'm solving for A. I get my acceleration to be 5.88 meters per second squared, and there's my answer. If in the previous slide you set each equation equal to A, then you would have solved for f of t, and then you'd have to plug back in to get your A, but it would give you the same answer. Okay, I want to remind everybody, please come in and talk to me for help. I feel like I have some holdouts. I feel like I have some people who may be struggling but are not necessarily taking the time to come see me. So I hope that you do that. I hope that this helps, and I hope you have a good night.